The next topic for us to discuss is called quantifiers. Quantifiers go hand in hand with predicates, and they allow us to express specific words in English, such as all, some, many, none, and few. There are three quantifiers I want you to know about. The first quantifier is called universal quantification. So the symbol here is like an upside down A, or you can think of it as a V with a line through it. It stands for the phrase for all, okay? And the shortcut here, if we were to use an equation editor, I know that this is the case for Windows. Apologies to Mac users if this is different, but it is slash for all. The way that we notate universal quantification is by saying for all x, p at x. And we are asserting that p at x must be true for every value of x, every value. The second type of quantifier is called existential quantification. The symbol for this is a backwards E, and it stands for the phrase there exists. As you might expect, the shortcut here is simply slash exists, and the notation says there exists some x such that p at x. It's asserting that p must be true for some value of x. Now some here just means at least one. It could be 1, it could be 2, it could be 3, it could be an infinite number of x's. At least one needs to be true. And the third quantifier is called uniqueness quantification. So this one has the symbol of the existential quantifier, the backwards E, but then it's followed by an exclamation point. And this stands for there is only one. So there is no shortcut here for that combination of symbols. You simply do the slash exists and then do the exclamation point. The notation here is suggesting that there exists only one x such that p at x means p must be true for one and only one value of x. That's the difference between uniqueness and existential. If exactly one is true, uniqueness is true. If exactly one is true, existential is true. But if more than one is true, the existential is still true, but uniqueness is not. Uniqueness implies only one. So with this in mind, let me draw some predicates with potential quantifiers, and let's discuss whether or not it's actually a proposition. Okay, I have 5 examples here. In the first 2 examples, we don't have any quantifiers. This just matches our understanding of predicates. And we already know that in terms of determining if these are propositions, the answer is no. They're not propositions, they are propositional functions. And those propositional functions become propositions once we assign a value to the variables. Now here's where it gets a little tricky. In the next 2 examples, I'm going to argue that these are propositions. You may be saying to yourself, well, wait a second, I still see variables, and those variables seem unknown. But they're not entirely unknown. We're actually quantifying them with either the universal or the existential quantifier. So the first expression is saying for all x, p at x. We can assess whether that's true or false by checking the values in our domain of x and seeing if they make p true. Similarly, the second one, which uses a different variable, and I did that on purpose to show that our quantifiers, we don't always use x, we can use y, z, p, q, x1, x2, whatever variable name you want. This one is suggesting that there exists at least one value of y such that q at y is true. Even though we don't explicitly know here what that value of y is, we can examine whether or not this statement is true or false. And it will be true or false, but not both. So these are propositions because we have quantified values for the variables. Now the last one here, you might have been saying, well, wait a second, that's the uniqueness quantifier. Why did we separate that from the other two? Shouldn't this be a proposition as well? And it turns out that this particular one is not a proposition. And it's not because it's uniqueness. It's simply because we still have an unknown variable. We have quantified the value of z, but we don't know what y is. If we have an unknown variable that has not been quantified, it is not a proposition. I'll just add the note, in all of these cases, it is a good idea that we specify the domains for all the variables. So for example, u of x or u of y, u of z. We need those domains. So next I'm going to walk you through 8 examples to see how we can use quantifiers and assign truth values to statements involving quantified variables. So number 1 says this: what is, for all x p at x, where the predicate p at x is equal to x is less than the absolute value of x, and the domain of x, u, is all negative numbers? Take a moment, see if you can answer that for yourself. So it turns out that the answer here for that quantified statement is that it's true. The reason that it's true is that the domain here matters. So it's basically saying, is it true that that x is less than its absolute value, where x can only be negative numbers? Well, of course it is. The value itself is negative, the absolute value will be positive, any negative number is less than its positive version. So that must be true. But notice that if we were to change the domain, that may not be the case. So if we let the domain of x be all real numbers, then this universal quantifier on p is actually defined as false because the positive numbers, this expression x is less than its absolute value, will not be true. All right, example number 2. What is the truth value of this expression for all y, q at y, where q is equal to y squared is greater than 0, and the domain of y is all integers? So it turns out that this is false, okay? And the way that we can prove this to be false is by using what we call a counterexample. A counterexample is one in which q will not be true, and then that means that it's impossible for all values of y to make q true. So in this particular instance, we can say something like, what about q at 0? Q at 0 is 0 squared greater than 0. That is false. The fact that it's false for that one example means that the universal quantifier must be false as well. Remember that upside down A means that all values of y must make q true. Number 3, what about the truth value of this existential expression? There exists some z such that E at z, where E denotes the statement z is even, and the domain of z is all real numbers. This one, I hope it's obvious to see that the result is true. If we let z be any real number, and the predicate we care about is that z is even, there are a bunch of real numbers that are even. The existential quantifier only needs 1. So we could use the example of z equals 2. When z is 2, E at 2 is true. The number 2 is even. So that makes the existential true. What if we were to change the domain here and say all integers, right? The domain of z is now all integers. This is still true, right? For the example I just gave, we could even restrict this further by saying all positive integers or all negative integers. In either of these cases, this particular expression is still going to be true, and all we need to do to prove that is to find one example that makes E true. Okay, number 4. Suppose we let p at x be the statement x plus 1 equals 0, and the domain of x is all integers. What is the truth value of the uniqueness quantification? So there is only one value of x such that p at x is true. This uniqueness quantifier turns out to be true. The reason that this is true is because p at x is true only if x equals -1. The fact that there's only one value of x, there's only one integer, that would make this predicate true means that the uniqueness quantifier holds. Notice if we change the domain instead of all integers and we said all positive integers, this would now be false because there aren't any positive integers that make the expression x plus 1 equals 0. So therefore, there's definitely not only one. Number 5, you'll notice I'm changing the way that these questions are asked. I'm changing the use of variables here. That's just to help you understand that we're not always using the same letters or variables. So given that t can be any real number, in other words, I'm defining the universe of the variable t as the set of real numbers r, what is the truth value of this quantified statement? there exists some value of t such that t squared plus 12 equals 7t. Pause the video for a moment and see if you can answer this question. Did you arrive at an answer? Before I tell you what it is, let me show you how I would solve this problem. So I'm going to move the 7t. I'm going to subtract 7t from both sides so that we have a quadratic. So it's t squared minus 7t plus 12 equals 0. And now you could use the quadratic formula to solve for t, but I really like to try and solve some of these in my head by saying, well, should be the multiplication of t plus some value times t plus some other value, so all equals 0. And what I'm doing here is I'm saying, well, what two numbers can go here and here such that adding them together gives me -7 and multiplying them together gives me 12. Can you see that if I were to put -3 and -4 here, at -3 and -4, when you add that together, it is -7. And when you multiply -3 and -4, you get 12. So this is the proper way to write this quadratic in simplified form. Now that we have this multiplication that must equal 0, one of those two terms in parentheses must be 0. This means that t could either equal 3 or 4, right? 3 minus 3 is 0. 4 minus 4 is 0. If one of those is true, the full expression will equal 0. So is it true that there exists a value of t that makes the quadratic hold? Yes, that is true. Notice that if I were to ask the uniqueness quantifier on this same expression, this would now be false. The reason it's false is because we have two values, 3 and 4, not just one. Uniqueness implies only one value for the variable could make it true. Number 6, given that the predicate s at x means x is a senior, and t at x and y means that x is taking y, write the following statement in English. There exists a value of x such that s at x and t at x and CSC 2100. Now technically I just said that expression in English, but that's not how we talk conversationally. So let's start first by agreeing on some domains, x and y. It appears that x is referring probably to students, so let's let the domain be all students, and y appears to be talking about courses, so let's let the domain of y be all courses. If I were to write this in a conversational manner, in the way that I would talk to a friend or a colleague, I might say something like this. At least one senior, that's the s at x, is taking CSC 2100. Can you see how that translation works? In order for this English statement to be true, two things would need to be true. There needs to be a student who's a senior, and the conjunction here, that particular student needs to be taking CSC 2100. Is this true or false? I'd have to go and check the roster, but I think for this semester, that might be false. I don't think anyone's a senior who's in the class. You can correct me if I'm wrong when I see you next. Okay, let's do two more. So write the following sentence as a mathematical expression. So this time we're going to go the other way around. So the sentence is, every student in this class is also in 2290. Now, we could just define that as some proposition P, right? And assign a truth value just based on whether or not that's true or false. However, quantifiers allow us to be more explicit. So let's first define some domains here. Suppose we have a variable x. We're going to let the domain of x be all students. I'm just picking up on keywords in the statement like students and class. So let's define a variable y to be all courses. And then I'm going to also define, let's say, a predicate t that operates on x and y. X is taking y. So a particular student is taking a specific course. Can you identify what the quantifier in this expression should be? This keyword here, every, should clue you in that we're looking at a universal quantifier. What is the universal quantifier operating on? Is it on the courses or on the students? I hope it's easy to see that it's talking about the students. Students refers to x, so therefore, we're going to say for all x, for all students, every student. Now, what do we know about every student? This is going to be a compound expression here. So the first thing we know about every student is that we're asking, are they in this class? So I'm going to say t at x, and then I'm going to put a constant here. We don't need a variable, but I'm just going to write out CSC 2100. That is this class. We need some knowledge about a person, a student X, taking CSC 2100. And then also we're going to identify whether or not that same student X is also in CSC 2290. Now, the question I have for you is, what should the logical operator be that goes between these two expressions? Should it be a conjunction or a conditional? Pause the video to consider which of these two options is more accurate. If you chose the conditional, you are correct. Let me explain why that is briefly. If we chose the conjunction, what we're claiming is that every student of all of the students at Florida Southern, every student must both be taking 2100 and they must be taking 2290. Well, there's only, like 50 students taking 2100? So that's not true for every student, right? There are many of your friends are not taking 2100. So that would make this whole expression false. So why does the conditional end up being more accurate? Well, recall that for the conditional, when the hypothesis is false, it doesn't matter if the conclusion is true or false. The whole thing is true anyways, right? If false, then the conditional is true. What that implies is that if you have a friend who's not in 2100, that's okay. They're not ruining the universal quantifier here because they would have a false hypothesis about being in 2100. Now, with that in mind, let's try this very similar but distinctly different translation. Suppose we have this statement: some student in this class is also in CSC 2290. So that keyword some should clue you in that we're going to talk about an existential quantifier here on x. And I'm using the same variables as before, x, y, and the predicate t. So some student will be taking CSC 2100. I'm going to skip the operator for a moment, but that same student, we need to know something about whether they're taking 2290. So now I will ask again, should this be a conjunction or a conditional? Pause the video to think about that for a moment. So in this case, if you guessed the conjunction, you would be correct. We need at least one student to make both sides of this compound expression true. The reason why a conditional would not work well here is because as soon as we found somebody who wasn't in CSC 2100, the conditional would be true for that student. But we haven't proven with that student that some student in 2100 is also in 2290. All we've proven is that there's somebody who's not in this class, right? And that's not the goal of the statement. So it's a little bit tricky understanding when to use conjunctions and conditionals. It's a decent principle that when we have the existential, we're probably not going to use the conditional in many cases, and the universal will probably rely on the conditional more. That's not a hard and fast rule, but it's just generally a good idea. Let's now ask ourselves some questions to increase our understanding of these new tools. First question, do we really need the uniqueness quantifier? In other words, anytime that we use uniqueness, could we have written that expression with the other two quantifiers and not needed this third unique version? So the answer, whether we need it, is actually no. We don't need the uniqueness quantifier. Let me give an argument for why that's true. Here's my claim. I'm claiming that the uniqueness quantifier of any variable x operating on a predicate p at x, that is logically equivalent to this other complicated expression that uses the existential and the universal. So let me read that out loud. It's suggesting that there exists some value of x such that p at x, so right, that should be true because uniqueness is saying, well, sure, there exists something, but there's only one. So how do we encode the idea that there's only one? So not only does p at x need to be true, but we can use a conjunction and say for all values of y, where the domains of x and y are the same, if p at y is true, the only explanation is that y equals x. Okay, think about a case where p had two solutions, x1 and x2. x1 would make the p true, x2 would make the p true. But when we do the universal quantifier on y, eventually y will end up being x2, right? x2 is a part of the same domain. x2 is going to make P true, right? So in the conditional here, we have if true, then is x2 equal to x1? No, it's not. So we've got this case here, true, and if true, then false. Well, that is false. Similarly, when x true makes p true, then the y eventually will become x1, right? That's one of the cases we need to check. And that will have an if true, then false conditional because it's not the same as x2. So this leads to false, right? That's why this expression is correct, because it only allows one value of x to make p true. And that's the whole purpose of the uniqueness quantifier. I'm only showing this to you to demonstrate that, in general, the universal and the existential are sufficient for covering all the cases that we could care about, but we often include the uniqueness quantifier just so that we don't have to write this complicated expression when we want to encode uniqueness. Next question. In general, our domains, those are the U's, those are going to be non-empty. In other words, there are possible values for the variables. But what happens if it is empty? So let's take both of those main quantifiers. So for all x p at x, and there exists some x such that p at x, what are these logically equivalent to? Is it true or false? Right, we're asking true or false. If the domain is empty, how do we encode that the domain is empty? Well, we would say U at x is equivalent to the empty set. So this symbol here means the empty set. This is the Greek letter phi, maybe? Like lowercase phi? I'm not really sure. Someone can correct me on that who knows the Greek alphabet a little bit better. But what if I told you that the truth value of these quantified statements was true for universal, but false for existential? Would you believe me? Think about that for a moment. If the first one is claiming that for all values of x, p at x is true, well, if there are no values possible for x, then sure, every possible value made p true. There aren't any possible values. So it's true. For the second case, I'm saying there must be at least one value of x that makes p true, but if the domain is empty, there isn't at least one value of x. There are no values of x, so none of them could make p true. I realize that might be somewhat unsettling. I'd be happy to discuss this more in person. This is just kind of a special case where empty domains make the universal quantifier true, the existential false. Speaking of domains, what happens if we want to restrict our domain? So what I'm describing here is that we can restrict our domain by placing a condition right after the variable that's called out in the quantifier. So let me give you some examples. Suppose I wrote that for all x less than 0, x squared is greater than 0. Notice how the quantifier operates on x, but it's actually on a restricted value of x. Now I'm saying x must be less than 0. And I'm assuming here that we've also provided some value of u, the domain. What I want you to see is that this whole expression, we could rewrite that. We could write that as the normal universal quantifier operating on x such that if x is less than 0, then x squared is greater than 0. Notice how the restriction just moved to be a hypothesis of a conditional statement. Okay, make sure you understand why what's written in green is equivalent to the expression in red. Let's try another one. For all values of y not equal to 0, y cubed is not equal to 0. So I'm restricting y to be values that aren't 0. And I'm placing that restriction immediately after the variable that's being quantified. We can also do this for existential quantifiers. So if I have there exists some value of z greater than 0 such that z squared is equal to 2. Now obviously the domain will matter here, but I think in many cases each of these I want to say is going to be true, right? When we square a number, it's generally greater than 0. So that should be true. If y, let's say y was like an integer value, if it's not equal to 0, then the cube won't be equal to 0. That should be true. And then if z is greater than 0, is there a value of z such that z squared equals 2? If we do integers, that would be false, but it would be true for real numbers, right? The value of z that makes this true would be the square root of 2. And again, I will note here at the bottom, just to drive home this point, we really should make sure to specify domains. If you're solving a problem and I don't give you the domain, it is very reasonable to ask for it because that might influence the truth value, as we see in the last example here. Next question. How do quantifiers relate to computer programming? Many of you are computer science students, and so I like to try and demonstrate how you've already done discrete math in your programming. You just may not have thought about it that way. If you're not a computer science student, you can tune out for the next couple minutes. But for CS students, we know that in a finite domain, that our universal quantifier is actually like a loop. So I want to demonstrate some pseudocode for how we would determine the truth value of some propositional function p at x. The way that we would do this is we would loop through the values of x, so that has to do with our domain, and for one of those values, if p, the predicate we care about, at x, if that's false, we're simply going to return false, right? The claim was that it must be true for all values of x, so if there's one where it's false, then the whole thing is false. And then we have the end of the loop here. If we've made it this far in the loop, and we didn't return false, that means that it must have been true for all cases. So the full quantifier will be true. We could do a similar approach for the existential quantifier. So there exists some value of x such that p at x, we loop through our domain, that's the possible values of x. And now instead of asking is p at x false, we're going to say is p at x true? If it is, we have found the existence of a value. So we're going to return true. If we make it to the end of the loop and we haven't returned yet, then that tells us that there were no possible values in our domain that made p true, so we return false. So anyone who's written code involving loops and selection statements in computer science has done discrete math. Next, let's talk about precedence. So all of these quantifiers, the universal, existential, and uniqueness, they have higher precedence than all of the other logical operators. Higher precedence. It means that we do them first in the absence of parentheses. So here's the implication of that. I'm asking, are the expressions for all x, p at x, or q at x, and for all x, p at x, or q at x, are those the same? Obviously, the only difference here is the parentheses, and it turns out that these are not the same. Okay, and here's the reason why. The universal quantifier will have precedence here. So we're going to assess whether or not for all x, p at x is true or false, but then we're going to do the disjunction of that with q at x. But q at x is not a proposition. We haven't quantified x, we haven't given a value for x. So this whole expression here is not a proposition. That's problematic. The one on the right is a proposition because we have parentheses. So you can envision a third predicate here, r, that's equivalent to the disjunction of p or q. And then this question becomes, for all x, is it true that r at x? That is going to have some true or false value. So this one is a proposition. When in doubt, put parentheses, especially if you have compound propositions that the quantifier needs to apply to. Now, logical equivalence in terms of quantifiers is important to discuss too. So statements involving predicates and quantifiers, they're logically equivalent if and only if they have the same truth value no matter which predicate is used or are used, and no matter which domains are used. So for instance, is it true that these two expressions are logically equivalent? The answer here is yes. Right? If there is some value of x that makes both of them true, or excuse me, that makes at least one of them true, then if you did the quantifier separately, so like distributing that existential quantifier in, that would still be true as well. However, if we did that on a conjunction, this is not necessarily true. It's not equivalent. So the left side is suggesting that there's a single value of x that makes both p and q true, And the right side is suggesting that there's a value of x that makes p true and a value of x that makes q true. So for instance, suppose p and q were the expressions that x being a person, likes to eat salad, maybe that's the p, and the q is likes to eat, or no, let's change that around. The p is that x likes to eat pizza. The q is that x likes to eat quiche. Right, we'll stick with the letters P and Q there. On the left side, we're saying there is at least one person that likes both of those things. On the right side, we're saying there's a person who likes pizza and there's a person who likes quiche. Those people don't have to be the same. So the right side could be true when the left side is not, and therefore these can't be equivalent. The last topic here with quantifiers to start is the idea of what happens when we negate them. So let me give you 2 examples. And for each example, I'm going to say you need to express the statement using quantifiers mathematically, and then we try and negate that expression. Okay, so the first one says, everyone in class will watch the Super Bowl this year. So let's define a predicate P at X to stand for the statement, X will watch the Super Bowl this year. And the domain of X is going to be people in this class. When I make the claim that everyone in class will watch the Super Bowl this year, I'm simply saying that for all X, for all people in this class, P at X must be true. Now, let's negate that expression. What does this version in green mean? It literally means not everyone in this class will watch the Super Bowl this year. If not everyone will watch it, do you agree that there exists at least one value of X such that not P at X is true? All right, let's write this expression out. There is at least one person in this class who will not watch the Super Bowl this year. Can you see how these 2 expressions are logically equivalent? If not everyone's going to watch, then it's true that there's at least one person who won't watch. So negating a universal quantifier led to the existence of the negation of our predicate P. Let's try a second example. Suppose I said there is no one who is a better quarterback than Tom Brady. And actually in this case, I don't think we need to negate the expression. I think it's already negated here by saying no one. So let me define Q, our predicate, at X to mean that X is a better quarterback than Tom Brady. And our domain of X is going to be all people. So the fact that we say there's no one, that's actually implying that there does not exist a person X that would make Q at X true. Right? There is no one. Let me submit to you that that should be equivalent to this expression. For all X, not Q at X. Right? If there's no one who's a better quarterback than Tom Brady, then for all people, none of them can be a better quarterback than Tom Brady. So the negation of the existence is equal to the universal quantifier of the negation. Let me, as a thought experiment, ask you what happens if we negated the uniqueness quantifier. Could we then turn this into a universal? I think the answer here is no, because if I said there doesn't exist one person who's a better quarterback than Tom Brady, yeah, so the negation of there being one person, exactly one person, could mean that there's more than one person, right? It could mean that there's no one who's better. It could mean that there are 100 people who are better. So I don't think that the uniqueness applies as much in this example. So where does this leave us? Well, it turns out that when we negate expressions in quantifiers, we can distribute that negation in the same way that we distribute negations into compound propositions. And you might recall that we used De Morgan's law to do that. So De Morgan's law also applies to quantifiers. If we are trying to negate a universal quantifier, the universal converts to an existential, and then the negation moves inside. If we negate an existential, the existential converts to a universal, and the negation again moves inside. So think about why that's valid. It actually goes back to our regular understanding of De Morgan's law. If we have a universal quantifier over P That's actually logically equivalent to saying that P at x1 is true and P at x2 is true, and so on and so forth for all possible values of the domain of X, this large conjunction. If we are to negate this, it's equivalent to negating the right side. But now hopefully you can see that negating that compound expression on the right, we would simply distribute the negation in and flip all of those conjunctions to disjunctions. Similarly, if we have the existential quantifier over some P, that's equivalent to the disjunction of all of the possible values of the variable x in our domain, such that negating the existential is equivalent to negating this large disjunction. So we would pass the negation through and we'd flip all of those disjunctions to conjunctions. All right, so that's the quick intro to the basics of how predicates and quantifiers can allow us to mathematically express more complicated ideas from English. This will be really important as we move forward with proofs and other techniques of propositional logic. Thanks for watching.